expert view on battery life and battery degradation. From the University of Liverpool, lecturer at the Stephenson Institute for Renewable Energy, Laurence Hardwick, who's going to tell us all about electric vehicle battery developments. Laurence.
Well, first of all, I'd just like to thank the organisers for sort of a brave decision to invite someone here who normally talks to a very academic audience, chemists and physicists and material scientists. So I'm here really just to tell you what the current state of battery research is at the lab level, on the lab bench. And so sort of the first question is why lithium batteries? And if we cast some of our minds back further to our sort of when we were at school and looking at the periodic table, and we see here there's lithium, it's the lightest metal. So if we want very lightweight batteries, we have to choose the lightest possible materials. And lithium being the lightest is a very good candidate, and this is the reason why you hear the name lithium batteries mentioned a lot in the media. Now, we're going through now sort of the greatest transformation in transportation since the early 1900s. So here we are in 2013. The majority of us are driving internal combustion engine cars, but there's going to be a transition, a very important transition, where we'll switch from internal combustion engines to electric vehicles, and the sort of time horizon there of up to 2030. Now currently we have hybrid electric vehicles, and sort of like the Toyota Prius, and these contain nickel metal hydride batteries. And because these are, say, for regenerative braking or, say, more efficient use of the internal combustion engine, lithium batteries don't really fit into this sort of niche market. However, where they do come in, which will see the majority of electric vehicles in the near future, is the plug-in hybrids, such as the ones we've heard about today. And these will dominate electric vehicles for years. So here we have a combination of a battery pack and internal combustion engine, and the challenge is to increase the size of the battery, or the ability of the battery to deliver as much driving range, and lowering the say the size of the internal combustion engine over the next 20 years, where currently, say for the Chevrolet Volt, it's you can get 45, maybe up to 60 miles driving range, but we really want to push the science and the technology to develop batteries which can deliver driving ranges of over 250 miles without having to charge. And then there's the final type, is the pure electric vehicle, where we completely get rid of our internal combustion engine, where we want to develop batteries which can deliver, say, charging. On single charge, you can drive 300 plus miles, that's 500 kilometers, and there are a lot of potential technologies, such as the LithiumAir Battery, which I'm going to discuss today. And also, I should also mention fuel cells, which will, are another sort of potential future technology, which is a lot of research and development is going on for these type of vehicles. But again, as mentioned earlier, there is the question of where do we get the hydrogen from, and also the sort of the network of supplying the hydrogen to power these cars. However, I'm very happy to say that if fuel cell cars come in, you'll still need a battery in a fuel cell car. So with all this, the battery is the barrier for a greater uptake of electric vehicles. And of course, as what we're all here today is this very exciting initiative by Northern Ireland is the recharging infrastructure which has been put into place. Now, we're all very familiar with lithium batteries. They're in the billions and billions of consumer electronics, mobile phones, laptops, etc. However, these types of batteries are very good for these sort of small applications, but we're asking a lot more, our batteries to do a lot more for electric vehicles. So how can we take what's sort of a consumer electronic battery power to electric vehicles? Now the cost will have to come down considerably, so from $1,000 per kilowatt hour down to about a fifth, at least a fifth, say 200 to 500 kilowatt hours. The safety of batteries currently, they have to be very high because we don't want anything to go wrong. But the safety for electric vehicles has to be even greater, that they have to be very safe if they're hit, because you're driving your battery around and you don't want anything catastrophic to happen when your battery is impacted, say, by another car. So safety is very key in developing new types of batteries. Now here we have what's sort of the energy density. Now this is what all battery chemists, such as myself, are very interested in, this number. It's how many watt hours you can squeeze into a kilogram of battery mass. And currently, with consumer electronics, we're between 100 and 200 watt hours per kilogram, but we want to drive this up to a target of 500 watt hours per kilogram, and this will deliver battery packs which can, on one charge, give us, say, this 300 miles without having to recharge. And we want our batteries, when we buy our electric car, we want our electric car to last maybe 10 years. And we want to get the cycle life, so notice when you buy a laptop, you maybe get 3 or 4 hours of charge before you have to recharge the battery, but then maybe in 2 years' time, it's down to 1 or 2 hours, and certainly there is some degradation in the battery, and this has to be addressed, especially if we because of this sort of cost implications of replacing the battery. We want the battery to last as long as possible. And again, when the battery manufacturer makes the battery and it sits on the shelf waiting to be bought, it has a certain shelf life. And we want to prevent the batteries from degrading even just by sitting idle on the shelf. And these are the targets that sort of electrochemists and material chemists are addressing currently in the lab to develop these new types of materials which can deliver these types of improvements. Now here is a sort of roadmap of different battery technologies. And we see here we have the Nissan Leaf, just as an example, and this is a fully electric vehicle and can deliver a range of 100 miles. And this is using current lithium-ion battery technology. Future lithium-ion technology can push this up to beyond 125 miles and maybe up to 200 miles. And this is what I'll just first touch upon some research going on in research labs in the UK. As Quinton has a sort of evangelical desire of convincing everyone to drive electric vehicles, I have a sort of evangelical desire of trying to just sort of educate everyone that a battery is not just a box with a plus and a minus sign on it. There's some very exciting and sort of very beautiful chemistry going on inside this, and I think also this can be communicated much better from people like myself, and I think this can also help convince people that battery cars are, the exciting reactions going on, which can make people, say, more enamored to this type of technology. So the chemistry for a lithium-ion battery is based on guest-host interaction. So we have a host material, and say for the anode, it is carbon, so we all have our pencils on the table containing graphite, and that's the anode material in the battery. And then for the cathode material, it's something, a layered material called lithium cobalt oxide. And sort of to champion the UK science, this was actually a material developed about 25 years ago in Harwell in Oxfordshire. So the UK certainly punches its weight in in its battery research. And this is the other host material. And the guest is the lithium ion. And so we have these, if you remember back to our school days, looking at the structure of graphite, it's a layered material, and it doesn't have any guests inside, but when we're charging our battery, either at a charging station or, say, charging our laptop, the ions in the cathode leave the cathode and are inserted in between the layers of the carbon. And this is where the charge is stored. Then when we're using our devices or driving an electric car, these ions then leave the carbon and are reinserted back into the host structure, which is this lithium cobalt oxide. And amazingly, this is a very reversible reaction. It can do it many thousands, hundreds and thousands of times without too much degradation. And this is the sort of exciting chemistry which is going on inside these batteries. Now, battery chemists like myself, we're not rocket scientists, and before you all run away to lunch, this is the only formula I'm going to show you today. So here's what we're aiming to do. We're trying to improve the specific capacity, so how many ampere hours we can squeeze into a kilogram of material of battery mass. All we're wanting to do is to increase the number of electrons or lithium ions that can be put into the material. So that's the sort of delta X, the triangle X. The 26.8, we don't worry about, this is a fundamental constant. And we have M for the molecular weight, so we want to, for the host scaffold, we want the weight of this material to be as low as possible. And then we can increase the specific capacity, which then relates to how much charge we can store, and then further down the line, how many miles we can drive without having to recharge the battery. So this is sort of the first bit of data from the lab. Now these are pictures taken by an electron microscope. Now we're all used to looking through a microscope, and we look at them. This uses light to increase the image, but here with an electron microscope we use electrons, and we can see to much smaller dimensions. Now, it may not be so clear on the images, but we're looking at a range of different nanoscale architectures. And sort of the smallest thing as humans can conceive is the width of a human hair, which is 1/10 of a millimeter. Now, these materials are 1,000 to 10,000 times smaller in dimensions, so they're really, really small. And one of the great things about sort of nanoscience, materials, is that the properties differ from bulk materials. So here we have titanium dioxide, a potential new battery material. Titanium dioxide is very cheap and very familiar. If we go outside, we see the white paint on the roads. That's titanium dioxide in. When we go away on our holidays, we put in sun cream. The white of the sun cream is titanium dioxide, so it's a very cheap and abundant material. And when we go to the nanoscale, we can insert double the amount of lithium inside. And some of the work going on in the UK is looking at different types of architectures for nanomaterials, such as you can have a simple nanoparticle, or you can have sort of nanowires, or a mesoporous structure. So this is, if you can imagine, a beehive. It has this sort of honeycomb structure, so we develop materials which the walls of this beehive material is in the order of 3 to 5 nanometers thick, and also nanotubes as well. And they all have very different properties. So here's the first sort of bit of data to convince you about all these new advancements. So if we take the blue line, so here we have the capacity on one axis and cycle number on the one hand. So what we want is to have a material where we have a very high capacity, and we cycle it a number of times, and it remains at a very high capacity. And the bulk material, as we see, it fades very quickly. So this is certainly not a good battery material. However, when we use a nanotube, and if you look at the orange line, we maintain a very good retention of the capacity as we cycle. So very specific nanoarchitectures are very important in providing a much greater capacity. And of course, as these are nanomaterials, we can get the lithium in and out much faster because the lithium has less of a length to travel. So therefore, if we want to recharge our battery, it's very good to have these type of nanomaterials because when we stick in the plug, we can charge these much faster, and then you can recharge the battery much quicker. And this is another sort of impediment for electric vehicle uptake is, people are lazy. They don't want to wait too long for their batteries to recharge. They want instant, they want to plug in, wait maybe 5 minutes, and then drive off again. So that's sort of in the near future. Now, the final part of the talk is to talk about something which could be a technology in 20 years' time. And this is the LithiumAir Battery. And as you see, that the potential of this battery is to deliver a battery pack for, say, Nissan Leaf scale electric vehicle, which would only need recharging after 300 miles of drive. Now, this battery has an equally exciting chemistry. So we have a lithium metal anode, we have an electrolyte which contains lithium ions, and then we have a sort of composite porous cathode, which comprises mainly of carbon, again, material in our pencils, cheap and very light, in a sort of very porous architecture. We can decorate this with a catalyst. And then when we introduce oxygen, the blue dots, we grow what's this very light material, lithium peroxide, Li2O2, the formula. And this, because of we're using very light materials, this can deliver a much greater capacity for the cell. And the remarkable thing is that when we charge the cell again, that we can remove all this material and release the oxygen again and have a reversible battery. Now, there are many very fundamental and for scientists like myself, very exciting challenges to overcome for this technology to potentially come to market in 20 years' time. Now, we see here very high capacity numbers. One of the greatest challenges is what's known as the voltage gap. So when we discharge the battery, we get 2.5 volts, but then when we charge it again, we have to charge it at 4 volts. Now, this gap represents inefficiencies. So you're having to put more energy into the battery than you're getting out, which is not an ideal situation. Now, back in 2010, we see another graph showing capacity against cycle number, and you see very high capacities to start with, but after 40 cycles, the cell is dead. But with a lot of very fundamental and very important scientific work, new materials have been discovered, and this is one example, porous gold electrode, which is, again, a sort of mesoporous structure where we have sort of voids in the order of 50 nanometers. And you see here that the cycle number is stable. So the fundamental research into different electrolytes, catalysts, and electrode design do deliver progress, and certainly in a sort of 20-year time horizon, these type of batteries could potentially deliver a much greater driving range for electric vehicles. So just to summarize, there's a lot of work looking at different nanostructures, and this is leading to an improved higher power lithium-ion battery. The LithiumAir battery, which I just described, could potentially deliver a step change in energy storage with practical 3 to 4 times improvement on lithium-ion, which would be transformative. However, there are many challenges to overcome before this is a commercial reality. So I'm really sort of telling you something which will be a potential future technology. And thanks to the UK Research Council, the fundamental research is delivering better quality batteries for a variety of applications, which also include electric vehicles. So just to finish, of course this work is done by a huge number of people and sponsored by a number of different agencies which are listed up here. I'd particularly like to highlight the EPSRC, which is the UK Energy Physical Sciences Research Council, which is supporting and increasing the support to research like this to enable that the UK can develop these new types of batteries. So for that, I'd like to thank you for your attention and for keeping you from the lunch, and just like to highlight that Liverpool University is putting a lot of investment into renewable energy technology, and when they've come up with a Stephenson Institute for Renewable Energy. So Stephenson's rocket was 200 years ago the step change in transportation with the Liverpool-Manchester Railway, and so with fundamental research and science we want to deliver this sort of step change in transportation for the future.